But as per our discussion last time, I thought I'd just provide for you this resource. Eric Swanson was he was one of the founding members of what became Cirrus Logic. He went all the way up to chief technical officer at Cirrus Logic, whatever, 90 something patents. He taught a grad level mixed signal design class. And then while he was teaching that class, he would come in and do a lecture in 445L about discrete Fourier transform. Unfortunately, he passed away in 2014. If I were to summarize what Eric Swanson wants you to do, he wants you to make a difference in the world. Don't just make money, make the world a better place. And so this guy's legacy was to spread joy and human, the betterment of the human race. So learn all your good stuff in school. Yeah, go out and make some money, but in the process, make the world a better place. Okay, so we used to have long conversations about all the things that we had left to do. Unfortunately, he died way too young. Okay, but that's enough of that. And so there's a couple of equations in here that are the basis of the discrete Fourier transform. I'm not going to do the whole thing because part of this lecture was modeling the A to D converter, because that's basically where his expertise was. But I'm going to show you his equations the equations for the discrete Fourier transform. And in there are the two fundamental things that I was trying to say, and that is you have a frequency range and a frequency resolution. In other words, you have a finite sampling rate and you have a finite sampling time. And those two go hand in hand to figure out the limitations of what. So this is the definition of a discrete Fourier transform. Now, in our implementation, the input, the little a's, are typically real sampled voltages. But from a mathematical standpoint, the little a's don't have to be real. They can be complex. And then it converts it into the frequency domain, the capital A, with the sub M, okay? And W, as you can see, is a unit one. These are points along the unit circle in the complex plane as a function of capital N. Capital N was now he uses he uses a little bit different terminology than I used yesterday when we get to the letter T, but the letter N is the same. They're N total samples, and that basically, the bigger the N is, the more W's you have, okay? And so again, that's the conversion from the time domain into the frequency domain. An interesting thing about this equation, you know that I'm all about units, okay? So what are the units of little a in our context?
Voltage.
So what are the units of capital A? Okay, W is, is a dimensionless complex number on the unit circle, okay? So the units of capital are also voltage, okay? Just, but, and then, as you're probably well aware, the conversion to the frequency domain does not lose any information. So there is an inverse that if you perform the inverse, you get back the signals. Yeah, not all transforms are like this, but this one is. So you can take a set of samples, convert it to the frequency domain, perform your filter on the frequencies and convert it back. It's not necessarily a very efficient algorithm, but it's possible. Okay. Okay. Most implementations of the inverse Fourier transform are actually the same function. All they do is flip the sign on their coefficients right here, and they actually can use the same function. Okay, so this is the part that I was trying to make a comment about, and that is the bin, the frequency bin. The numbers you get in this, the numbers you get here, these little m's, are the amplitudes in the frequency domain, and those little m's are the equivalent frequency at bin m is m fs over n. So the resolution, now this is where he's got a different n in his not a different n, different t. Okay, in his definition, t is 1 over fs, and in my definition, t was all of n. But nevertheless, it's the same equation. 1 over the total time sampling is the frequency resolution. And then, okay, what's interesting here? More stuff interesting. I've already said that, and that is if the, oh, I didn't say it yet, but if the inputs are real, in other words, if A sub n are voltages, or raw A to D samples, whatever, if they're real numbers, then the transform, it can be broken into two parts, from 0 to 1/2 fs, 1/2 n, and 1/2 n to n. They're complex conjugates. They're mirrored complex conjugates. In other words, the frequency bin at 1 is the, if you have 1,000 points, the frequency bin at 1 is the same as 999, at least in the amplitude. In other words, you get a mirror image. So we generally don't plot that half. We just plot the first half. Yeah, and again, the units of this. It's interesting that there's something weird happened, right? We put in 1 volt RMS, and we got out 7 over 7, 700. I mean, we got out 700, and that's because it amplifies times the bin size. So that's okay. Okay, I probably don't want to do that one. I'm going to skip a bunch of slides and go to the last thing you probably should remember about the Fourier transform. I left them all here for your enjoyment. And that is, okay, let me do this one. I'll do this one. Let me do this one. In order to actually plot it on the log scale, as you know, we can't take a log of something that has units. So typically we find something, an equivalent full scale amplitude, and put it in the denominator before we do the log. So this is a constant associated with the way it was sampled. When it's called decibels full scale, and that typical spectrum analyzer does that for you. Okay, that's leakage is where I'm going with this. And we sort of did a hypothetical question when we had a frequency resolution of 1 hertz. What happens if you put in yeah, if I have a frequency resolution, I'll use his, yeah, so we'll go back to, if I have FS equals 1000 hertz, N equals 1000 points, then my delta F was 1 hertz. 1 hertz. If I put in, 100 hertz, which bin is going to have the, if this is just M, which bin is going to have the bump in it? M equals what?
50.
Okay. The equivalent F is M Fs over N. Okay. So this is 100. If I put in 101, but I'm going to get the next one, right? So it's going to jump to the next bin. If I put in 105 hertz, now I haven't violated the Nyquist theorem, right? F equals 105 is less than 1/2 FSM, half the sampling rate. What, you know what'll happen? What's this going to look like? There is no place to put 105, okay, in my plot. Always try it. It's going to be, of course, sorry, it's not continuous. Even it's going to have all of them. It'll spread all over the place. You can't resolve this waveform. And so typically what we do with a transform is window it. Oops, I can't see that color. Red, black, red, black. We window it so that we get just these two. Okay. And that's what I'm about ready to show you, windows.
What's the difference between the 101 and the 105? Why can we
Oh,
resolve?
101, I'm sorry. Yeah, thank you, stupid Valvano. That was what was going through my mind. Sorry, thank you. Sorry, I didn't mean to confuse you. 105 would have been fine. I meant halfway between. I am rationalizing both I'm rationalizing both experimentally, like this one, and theoretically, like the equation, that you cannot distinguish 100 hertz from 100.5 hertz. You can distinguish 101 from 100, or in your case, 105, but 100.5, halfway in between. Sorry. Thanks. I'm glad you brought that up then. That would have been stupid for me to have left it.
What resolution would you need? Like 2?
Sure. Okay. So yeah, there's a great exam question. That's a great exam question. Okay, so let me pose it as a rhetorical question, not for next week's exam, But for the, all right. What if I asked you, uh, I would like to resolve these two frequencies. What's the, there's more than two, there's more than one answer. But what are the fundamental equations that I have to set up associated with these two numbers? The sampling rate and the number of samples. Fs is greater than what?
Nyquist.
Yeah, this one, 2 times the largest frequency. And that's has to be not has to doesn't. I'm not saying equal to. Actually, I'm saying strictly greater than. Okay, but it's not necessary. And then, what can you tell me about Fs over N? Well, it has to be, sorry, less than. And this is less than or equal to. This is the frequency resolution.
It has to be a half a hertz, right?
Half a hertz, yeah. So is that the question you asked? Maybe it wasn't.
I think he was asking what the sampling frequency would be.
Well, the point is you have two, count them, two things you have to, and obviously in my, not in Eric Swanson's, but in mine, the total time, okay, was N over Fs, right? The total time. The total time duration, okay? You have two decisions to make. Now, there are three things here, but there's only two things, right? These three numbers, these three things come from two decisions because of this equation. And you have to decide them both. And your Fs, sets your frequency, range, and your total number of samples sets your frequency resolution. Okay, I beat that to death. Okay, so let's go back. So to solve that problem, there's windowing. And so basically before you do the transform, just so things like 100.5 don't get stupid, you basically take some function, and there are dozens of these functions that you pre-multiply. Now this is in the time domain. This is in the time domain. And that causes the two ends to match up when you, because the, yeah. Let me do a yeah, let's go back to Fs equals 1000 hertz. And let's put in F equals, yeah, first I'll put in 1 hertz, and you can see this is going to be fine. Okay. And so if I've got 1 second here, okay, N equals 1000 still. And doesn't matter where I start, I'm going to get exactly one waveform here. Right? Amplitude versus time. But if I have let me do an easy one. 1/2 hertz. What happens? What does it look like now? Right, I only get 1/2 hertz. Looks like that. And so when you do the discrete Fourier transform, essentially what happens is it takes your window, which is finite size, and repeats it infinitely in both directions. So the black one went like this, but the blue one looked like that. So it's no longer a sine wave, right? It looks the equivalent thing. I'll zoom out for the blue ones. You're basically taking the transform of that, which is no longer a 1/2 hertz sine wave. Which is why it leaks. But if you were to multiply it times this before you do the transform, it doesn't look so stupid. Okay. So you will
The
find
windows were to suppress edge effects, like
yes,
discontinuity
yeah, that's
effects at the
effect.
edge.
Yep, exactly. That's my point. This is the edge effect right here. Yep. So you'll find that the windows typically have very low amplitude at the edges, just so that, you know, so that, yeah, so because when you use a spectrum analyzer, you're not necessarily synchronizing your data sample with the signal. Well, anyway, so for transforms have windows too, and that's this thing, the transform of this here is not gonna look pretty, okay? And that's leakage. That's spectral leakage. All right, let's go back to. So I just one last thing about transforms. Make sure you window it. All right, so I renumbered the slides to stick this one in there. So next year when I teach it, I'll do it first. And I don't know if I left my pen. Yeah. I leave myself a star. Where far we got? So yeah, to say it like a 15th time, and that is you've got to know both the frequency limit and the time limit, because you don't have infinite time or infinite frequencies. Did I fix that one? And yes, that's right. Samples per second. Yeah. The other thing when you read this chapter is the point I was trying to make is bandwidth is a very elusive term of what they mean. But in understanding the Shannon channel capacity, you know, they're looking at the pulses. You know, it's encoded at some frequency band, and there are outputting so many pulses per second, and that's that FP here in this context. That's the number of frequencies that are, and this is the Nyquist theorem, okay, saying that the bandwidth of the channel, the maximum frequency, is 1/2 FS. Okay. And here's where we left off last time. Yeah, that's the same frequency. Okay, so here, this is Bill Bard. We've got a little bit of Eric Swanson to, okay, so in summary, the most important thing that Eric Swanson said to you was what? The most important thing in this slide deck here was what? Come on. If Eric Swanson wants you to remember something the rest of your life, what's that? It's not the discrete Fourier transform.
To do good.
Do
Not-
good.
not-
Make the world a better place, you know?
I'm doing
Take
too.
all of your skills and all of your knowledge and all of your resources. Yeah, make money along the way because you have families, etc. But really, your mission in life is to transform the world into a better place. Okay, that's the most important thing. Now we got a message from Bill Bard.
Wait, was that really the most important thing from that slide deck?
Yes, it really was the most important thing.
Huh.
It may be the most important thing you get out the whole semester. Because, yeah, it's a grad class. I'm not going to teach anything. You're just going to grow up and go out and do good. No, it really was the most important thing. Thank you. I meant it. He was a very intense man, if you can sort of get the, yeah. Yeah, like I said, he was chief technical officer at Cirrus Logic and also taught grad classes here. So, okay, so now we're going to have the message from Bill Bard is a little less intense. Okay, this is one of his slides. And I'm just pointing out that, yeah, there's a lot of definitions for bandwidth, okay? And be very careful of what it is you're saying. Now, so far until this whole chapter, I've been using bandwidth to mean bit rate, how much information was transferred per second, okay? But these bandwidths here are more like the Swanson bandwidth, and that is the range of frequencies with which the channel can pass data. And so the bandwidth here is more associated with the maximum frequency that can be transmitted in the channel. But they're not all the same. Okay, I'm 1, 2, 3, 4, 5, 6 different bandwidths, depending upon exactly whether you're measuring power or nulls or, you know, again, I'm not, yeah, so they're all related. These 6 are all really related to each other, and they have to do with amplitude versus frequency in the spectrum in terms of either gain or signal amplitude. But I'm just warning you, the world is not. And so again, the bandwidth here in this section, in this chapter of the book, is associated with gain versus frequency, okay? And so if a channel can pass from 0 to B, we're going to define B as the bandwidth. Now it often goes from B1 to B2, in which case the bandwidth is B2 minus B1. But, all right, so, and now we're going to basically go through the steps and we'll get to the Shannon-Hartley theorem. And again, the FP is the pulses per second, okay? So we send a pulse and we send another pulse. And this time is 1 over FP. Okay. And this is a typical, this is what you would see as a voltage on a RS-232 non-return to 0 RS-232 line, where it goes from -6 volts to +6 volts. And this here is the baud rate. So if you think of a serial line, you can think of the bits per second, and obviously we could use the Nyquist theorem to to determine how fast can I run a serial port line. How fast can I run a serial line? What's the maximum baud rate? Okay, so
It depends on the,
depends on what? Yeah, it's right here
I
on
mean,
the.
it depends on the channel and
Depends on what of the channel. What do I need to know about the channel?
the bandwidth, the
The
filter
bandwidth. Yeah,
parameters.
you know, that's the answer to the question I just asked, right? The maximum, because on a RS-232, on an RS-232 line, okay, you're sending 1 bit per pulse, right? Encoded as a non-return to zero plus or minus 6 volt voltage. And why does it, what's this plot mean? What's the difference between this plot and that plot?
The ideal versus the received.
Yeah, so this is the transmitted, this is what was sent, or the ideal, what we tried to send, and that's what we received. Okay. And why does it look all funny?
Capacitance effects and
Yeah, the bandwidth,
filtering effects.
the signal. Either one of these gain versus frequency plots is going to cause that to be the output, because a ideal signal with a square pulse has got infinite frequencies, and as you get closer to the bandwidth, you're going to lose you got the primary, but you're going to lose the harmonics, and so you'll basically end up with a sine wave, which is fine as long as you're passing FS, right? This is still works here. You just got to decode it. So again, the channel has got a gain versus frequency, which is going to distort your signal, whether you got an RS-232 line or a wireless, you know, wireless thing. All right, so that's so the line rate is going to be the number of bits per second, okay? And the FP is the pulses per second. In this case, they're the same, because in this encoding here, we're going to send 1 bit per pulse. So how do we go faster? How do we go faster?
Better transmission lines.
Okay, you can increase the bandwidth. Fair enough. Yeah, increase B. If you can increase B, you could increase F. All right, you could. What else could we do?
Multiplex.
Oh, more lines. Okay, yeah, that's multiple in, multiple out. MIMO. Or MOMI, I forget. There's one with a MIMO. Have multiple channels. Yeah, you could. Yeah, I'm not sure I got that right, but if you have multiple channels, you could go faster. But where I'm going is let's encode more bits per pulse. So if I just, rather than sending plus A and minus A, what if I sent minus A over 2, A over 2, and A, okay? If I could encode 2 bits of information in every pulse, then I could double the, you know, the effective information rate, R.
Doesn't the error rate go up though?
Of course, but that's the whole essence of the channel Hartley theorem, is how many bits can I put in there? Okay. How about let's just go back to what you know about let's go back to your serial port. Do you think with a 50-foot cable and an RS-232 line, you could tell the difference between -6, -2, +2, and +6?
I don't know, am I running next to a motor or in a factory? I mean,
Yeah, well,
is it
shielded
a
cable.
shielded
Yeah, that's
cable? I mean,
exactly
even
the
that,
point. That's exactly the point. You want to know what the signal to noise ratio is. Yeah, you're just deriving this channel capacity. The answer is you might be able to, okay? Or you might not be able to. Yeah, fair enough. We're just gonna, yeah, we're gonna get there, okay? But we're gonna try. Shall we not at least try? Okay, so little m is the number of bits in each pulse, right? So we have again, the pulse rate is the baud rate, if you'd like, the rate in which it sends pulses, which is limited by the bandwidth. But I'm going to encode more bits into each pulse, call each thing a symbol, right? So these are the symbols. And now I've got, if I just do this one little thing, I've doubled my information rate. Okay? So well, or whatever m is. Okay? And again, this is the maximum here. That's the maximum because this is FP. All right. But obviously, yeah, you know, you're not going to let me say that m could be infinite. Okay. No, because of noise. Okay. M is limited. This is limited. And that's the essence of the Shannon channel capacity. Before we get to the Shannon, we're not going to limit it. We're just going to define it. Okay. Now, in the previous example, I had in this example here, I had minus a over 2, minus a over 2. I had 4 things, but they weren't equally distributed. Over here in this one, I did equally distribute them. You see that? These are all delta 4. And so if I were to take a dynamic range of the signal, and this could be phase or voltage, depending upon how you're encoding, of course, but you have a signal dynamic range, and then you divide it up into delta V spots, right? That's going to give you one, right? So here, A over delta V is 4, right? I got 4 delta V's in an A, but I've actually got 5 codes, right? M equals 5 in this case. I get 1 more code. Okay. And the equivalent number of bits, obviously, is just the log base 2 of M. And now this is the, okay, so yeah, I already answered this question. Why is it +1? Is because we have the bottom one and the top one. Yeah, this is the actual line rate. Again, line rate is data rate. This is bits per second. And again, this is the pulse rate here. That's the number of symbols per second. And R is the data per second. And so remember where this came from? So why did we go from, how did we get from this equation to that equation?
Nyquist.
That's the Nyquist theorem. So the Hartley law is just a duh law. There's no sort of help in how to choose M. right? There's no fundamental help in how we choose M. It's just sort of, we built it, what did I have? Okay, kind of thing. But that's the Hartley law. And as you pointed out, the problem is noise. And we saw that in the last, there's a couple more cool slides in this one about errors. And the signal to noise ratio is one way to, sort of get a sense of how big can M be. What's the limitation on M? Because from a fundamental thing, in the context of the previous slide, okay, the signal was A. That was the dynamic range, right? The signal was A, and the noise is going to give you a sort of an understanding, a limit, a whatever for how many bins can I, how many different places can I divide it? And so this is sort of an illustration. If I had this much noise here, could I, in other words, I'm going to take this noise and I'm going to add it to these signals. And if you saw these, this is amplitude. This is amplitude versus time. Okay, if I gave you just one of these, yeah, you could distinguish from the other, right? Because the separation between these are bigger. And right over here, okay, right over here, I do the same sort of thing. What do you think? Could I tell them apart? Could I have twice as many bits? If I gave you this as a function of time, could you distinguish those 8?
Tougher.
Probably.
Yeah, probably. Yeah, sure. Fine. Fine. Well, what if I made the noise bigger? Okay. Now this one would probably work. Now they don't have to totally separate, right? I mean, they can overlap a little because you are sampling it, and yeah, you probably could, but over here you probably cannot. I'll just draw 2 of them. You probably would. Now, if I gave you one of those 2 waveforms, you probably couldn't tell me whether it was 7 or 8. Okay, you probably couldn't. Okay? So there is a limitation. Noise will limit the number. Will limit M.
If the noise is centered around a certain voltage, couldn't you take a moving average? Or is like, what's the...
Sure, no, totally right. No, so it's a good, all right. What does, okay, so now you just said, hey, John, what's the central limit theorem? Okay, so if I were to average, that's a wonderful thing, okay? If I were to average, what am I essentially doing?
Reducing bandwidth.
I'm reducing bandwidth, which means my FP went down. If you do an averaging, you're gonna take fewer, your pulse rate is gonna be slower. So a averaging filter does exactly what your intuition is saying. It does improve signal to noise ratio at the cost of slowing down the pulse frequency. Yeah.
It makes sense.
Yeah, and it may come out better or worse. I'm not sure, but you're going to try it. Okay. Yeah. So it's limited by noise is what I'm trying to say. Okay. And so, yeah, what's the equation? Okay. So, if these are the, right, if these are the M's, right, if this is the delta V, okay, and I need the delta V to be bigger than the noise, okay, and so this is my signal. So A over N is the signal to noise ratio. And boom, that's the Shannon channel capacity. Now this, okay, so we gotta work backward. This SNR is not in decibels. This SNR is in volts per volt or watts per watt. It's not in decibels. And so if this is that ratio between A over delta V, okay, where that's the maximum, so for instance, here's a modem wired telephone channel answer, okay, and that is if there are 63,000, if the ratio is 63,010, if there's 6,000 different bins that I can assign for bits, okay, that means there are 6,011 different, I'm sorry, if the ratio is 6,310, there are 6,311 bins. And I don't know if the +1 is a big deal, but if I take the number log base 2 of this, I get that little m. And now since we're looking at the limit, the 2 went away. Notice that in the previous Hartley theorem, there was a 2 here, okay? And the 2 is gone. And this is the, again, this is the frame rate. This is the frame rate. And the maximum frame rate here is going to be the bandwidth and not to the bandwidth. And that's the Shannon channel capacity or the Shannon-Hartley theorem, this one right there. And it's the intuition which if you want to go faster, you want to improve bandwidth, and you want to improve signal to noise ratio. And this is not actual, this is sort of a theoretical limit. That's what this is for. Okay. The book has got some examples associated with wireless stuff. These data points I got from Bill Bard when he taught this lecture. Bill Bard is a happy man. He owns a farm. He retired and taught himself how to weld. Yeah, so there's a Bill Bard lesson. Enjoy life tremendously. He's a pilot. He's built his own airplane and flew it. Taught himself how to weld. And so here was a 60-something-year-old professor going to ACC, taking welding classes with the young puppies. That was a fun thing to tell me. So I enjoyed my time. He used to teach 445L with me. And so, yeah, so these are examples from Bill Bard. Okay, so now we got a couple more. Yeah, question on the channel.
Oh, yeah, from a dimensional analysis standpoint.
Oh, yeah, good.
You have kilohertz times bits per second.
Yeah, sure, but that's fine. What are the units of what are the units of kilohertz?
1/seconds.
Yeah, 1 over a millisecond. What is the units of this box?
Shouldn't it just be bits?
It's bits. Is that not bits per second? Oh, you want millisecond, bits per millisecond.
No,
Yeah.
you have it times 12.62 bits per second on the, shouldn't that just be bits?
No, absolutely. Absolutely. Yeah, I see it. I see it. Yeah. Yep. Right here, that. Happier?
Yeah.
Yeah. Yeah. Thanks. Thanks. Yeah, I am. Yeah. Hey, one thing you'll talk about me when I'm very nostalgic today. I guess thinking of Eric Swanson has been very emotional for me. But yeah, so yeah, I'm thinking about what's your purpose in life, right? So, yeah, you can remember dimensional analysis. All right, a couple more topics here in this chapter before we go on to the fun stuff in the next chapter. They define bit error rate, which is a probability that you get an error. So yeah, the example in the book is crappy. Why did they do 5 errors? Let's do 4 errors. I just copied the example out of the book, but it's better. It's ambiguous. It's whether it means the accuracy rate or the error rate. But they mean the error rate. So the probability in this context is 4 bits out of 10 got flipped. Okay, and as you probably already know, what we just did, the channel noise, all the places that can can corrupt your data, interference with other EM in the same spectrum. Fading is what happens if the signal shows up at your antenna in 2 different ways, 2 different paths. Then the amplitudes don't align or they don't sum. Sometimes they can subtract. And then the attenuation is just that 1/r squared. And then over on the right-hand side, all the ways you can improve bit error, more power, a better antenna on the receiver, using a different frequency. That is something that I've noticed over my 66 years is every 5 or 6 years, they add more frequencies to make it less interfering. And then here's a cool quiz question for this is design me your own error. Now we're looking for error correction codes. Okay, I send 1,000 bits. There will be bits in error. There will be errors, but how do you correct for it? Okay, so in other words, here's the quiz question I'm going to give you. You're going to send 1,000 bits, and let's say you've got 3 bits will be corrupted. That's a typical 0.3%, whatever that is, bit error rate. And you're the software engineer on this project, and so how do you fix it? Without doing a Google search to look up how they actually do it, because this is obviously a rich field of communication called error correcting codes.
You tell the hardware guys to do better?
No, it's your fault. Ishan, no blame and somebody else.
I mean, the receiver doesn't know the truth, I guess, is the fundamental problem.
Yeah. But I gave you an easy problem, and that is the bit rate, the probability of error is very low. Okay.
But
To
do you
detect
have like,
errors or correct them?
Either. He said, do I want a correcting code or a detecting code? I don't care. It turns out, because if I can detect it, I can ask for a retransmission. Yeah, they're a little bit, it's a little bit easier to detect an error than it is to correct it. Yeah, so yeah, so
I mean, like send a checksum packet or something. And if,
Yeah.
you know, and some of you who checked out lab 1 know that a checksum isn't going to catch every error, right? Well, 3 bits a checksum would catch.
Yeah, if we have a 0.3% error rate, then a checksum often enough in
Yeah,
all likelihood.
often enough. Yeah, see, so that's good verbiage. That's good verbiage. Yeah. Yeah, so, you know, yeah, checksum is not a bad for detecting. Sure. Let's go, what other detecting mechanisms do you have? Yeah, sure, detect. So that'll work. Do that. Checksum, for those who aren't following along, is just you add up all the bytes and do a modulo addition on that, and and send the checksum along with it, so they can do the receiver can add up all the bits as well. So you sum all the data bits as the check, and you ignore the overflow, right? So if this is 8-bit data, this could be a 8 or a 16 or a 32-bit add, 24-bit add, or whatever. But checksum is not guaranteed to catch all the errors. But you know, this low of a rate, it probably most of the time it does. Any others you've seen?
Set deck, maybe.
What's that?
Second error detect single error correct.
I know, but what's the? Okay, so yeah, you don't. All right, so yeah, send me a link on that. We'll put it in here. I don't know that one.
Okay.
I do, you know, I'm just.
Could you use a Hamming code?
Yeah, sure. There's a whole bunch of codes that can detect and correct. Okay, that's my point here. And yeah, it's.
I mean, what are they?
I know the point is I don't want you to look them up. I wanted you. The point of this was for you to invent one. Yeah. It's a grad class. Yeah, you can look up the, yes, I suppose if you want a really good one, you should study all of them. Yeah, my favorite error correcting, 1-bit error correcting code is parity. So if this is my data packet, okay, I will add bits to each byte. And I will add bits to each message. For example, parity is 1 bit here. Basically, exclusive OR of the bits in this direction and exclusive OR of the bits in that direction. And then any 1-bit error here can be corrected. Yeah, there's a parity.
Are you sending the packet twice or?
Oh, okay. So an 8-bit packet, okay, 8 times 1,000. I'm going to send 9 bits times 1,001. So I'm going to send an extra, whatever that is. I'm going to send, I've got 8,000 bits in my packet, and I'm going to send 9,009 bits. Okay. I'm going to send more bits than I need, just like you did with checksum, right? In checksum, you know, you took 8,000 bytes and then sent 8,001, right?
But
You
that
add one
catches,
byte.
oh, that catches all 1-bit errors. Like, but if 2 bits are flipped,
Of
it
course.
might.
Okay, but okay. So what is it? So what happens? Okay, fine. I like it because it's mathematically simple, as opposed to the other things which are a little more complicated. 1-bit error, pick a bit anywhere. Okay. The consequence of it is this one is going to be wrong, and this bit here is going to be wrong. So I know which one to fix. Okay. So what happens in a 2-bit error? Chances are the 2 bits are not on the same row or the same column, in which case I can correct both. I can detect it. I can't correct it. Okay. I can detect any 2-bit errors. Okay. You take any 2 bits in this code and you flip them, I can tell you the code is broken, that the message is corrupted. I can detect every 3-bit.
If they're in the same
I
byte,
can't correct it, but I can detect it.
if they're in the same byte, if you have 2 in the same byte, you can.
Sure. Because if they're in the same byte, okay, let's do it. Let's bring it over here. Let's bring this one wrong and that one wrong, right? This guy is correct, but these 2 are incorrect. Right?
How was that end one calculated?
This is exclusive OR in both directions.
Oh, you're exclusive ORing the bytes.
And the bit.
Oh,
Exclusively the OR in both. Then it's basically parity, right?
okay, I see.
Parity code, but it's a parity in 2 dimensions. Parity in this dimension, right? I took the original data, I added 1 bit. Now you can add 2 or 3 bits if you want. Okay, could. But then I added 1 byte or 1 9-bit thing. And so it can detect 1 bit, 2 bit, 3 bit, and correct 1 bit. Let's see. But a 4-bit error could possibly go undetected. Okay, so let me just give you one theoretical framework around to think of this. So this is one of my favorite. I like to do it because it's easy to explain. Okay. If you think of okay. I'm going to do this in 2 dimensions. Is if I take 2 binary numbers, okay, I take 2 n-bit binary numbers. That are off by 1 bit. What sort of logical analogy might you say to these 2 numbers? They are what? And the answer is their distance from one to the other is very close. So if I were to plot M and N in some sort of dimensional space, which is probably 8 dimensions because I got 8 bits. But if you were to visualize M and N in the noise space, they are very close. Their distance, if you'd like, their distance is 1 bit. And distance is defined to be how many bits do I have to flip to go from one to the other. Whereas if I were to look at P, right, which, let's compare it to M. If I looked at P, when I have 1 0 0 0 0 1 0 1, okay, P is further from M, okay, so, and further from N, so it's 2 to get to there and 3 to get to there, okay, so P is closer to M than N, okay, and so in order to separate M and N and P. So if I look at if I looked at a non-expanded code, okay, and if we go back to my friend N, okay, how many things, M is close to it, but there are some other things that are also close to it, right? There are seven things. 1, 2, 3, 4, 5, 6, 7. And now I'm very crappy drawing 8-dimensional space, but there are 7 other packets that are very close to N that are a distance of 1 bit. Okay, you see that? Right, all the numbers that are, take N, flip 1 bit at a time. So that's me, that's 8 actually. I've got not 7. I got enough? 1, 2, 3, 4, 5, 6, 7, one more. Okay. So for any one packet, there are 8 brothers, if you like, that are 1 bit away. Okay. This is a very vulnerable code, right? And so in order to solve this problem, in order to solve my 3-bit problem, okay, that's the one I posed to you. What you have to do is, again, now it's no longer 8-dimensional space, it's probably 11-dimensional space, okay? So now I'm gonna give you 11 bits to work with, okay? And now I want to make sure that every other packet is at least 4 bits away. Distance. And therefore, any 3-bit code, any 3-bit error is going to be detectable. So the distance from M to all the other packets, and all I got to do is add more bits. If 11's not enough, use 12. Here's one you already know. What if I use 24 bits? What could you do?
For 8 bytes of useful information.
Yeah, for 8 bytes of useful
Or
information.
I mean 8 bits of useful information.
8 bits of useful information. 1 byte, 24-bit encoding.
Do it a couple times.
Well, I do it exactly 3 times,
Yeah.
right? And then I vote. Unfortunately, it's not a very efficient process because I can correct 1-bit errors, but I can't. I can detect 2-bit errors. I can't correct it. 3-bit errors could go undetected. So it's a lot of bits for not much performance. And so yes, there is a whole bunch of codes that that help you. And so they're associated with this essence of distance in multi-dimensional space. So if I have a 12-bit frame, this is a 12-dimensional plot, and you can think of the Euclidean distance from one packet to the other separated by space that can't be packets. Enough of that. That's a fun exercise. This is out of the book. It's sort of a duh plot, but and so these are 1, 2, 3, 4, 5, 6, 7, 8, 7 different encoding schemes to do exactly what we were just talking about. And that is, can we reduce can we improve error rate? Can we make it better? What can we do to make it better? Okay. And so there are three things associated in this plot. First, let me define the terms first. This is the number of watts per, joules, watt seconds per bit, right? This is the energy that I'm going to put into each bit, not necessarily each packet, because a packet might have multiple bits. And this is what, what Austin was answering, and that is if you do filtering, you're going to increase the time to do it, which would improve the energy, right? So if I double the amount of time, I have double the amount of energy, but I did have my bit rate. Okay, that's in joules. And then associated with, this is the good thing, right? This is the good part. And there's the bad part, that's the noise. And it's in noise density. So this is basically, you take a spectrum of your noise and non-dimensionalize it in watts per hertz. That's the essential spectral density of a noise signal in watts per hertz. And then you divide the two. And this is a dimensionless efficiency associated with the physical channel. So this is a non-dimensional way to describe the efficiency of converting bits through a noise channel. And so the units of this. Okay, so what are the units of, what is a watt second per watt hertz? Right. Joule divided by watt hertz.
Dimensionless.
It's dimensionless. Okay, so that's why it's called an efficiency factor. So that's this thing. So the next thing we want to do is sort of get a sense of what is, where's the good stuff? Which way is, I'm going to draw good and bad. Okay, as sort of on this plot. What is a better power efficiency? I would like to have a large what and a small what, right? I'd like to have lots of energy in the bit and very little noise. So this is the good direction, and that's the bad direction, okay? Let's do the same thing up here, and that is, this is the probability of error shown as a dimensionless crap. What it did is a PB stands for probability. And so a probability of 1 is what? If I said the probability of a bit error was 1 or 100%, is that good or bad? Bad, okay. So this is the bad way. And this is the good one. Okay. So normally we plot good up and bad down, but this is an error rate, not success rate.
If your probability of a bit error was 1, couldn't you just assume that everything gets received inverted?
Oh, nice. Nice. Oh, yeah. You're a scoundrel.
Just to go back to Q-Sean's point about telling the hardware guys to do better, how many of these protocols have baked in hardware correction? Like
Oh,
my
yeah.
old
No,
my
no,
old modem had like hardware error correction, but like just sub gigahertz, just Bluetooth, like what?
yeah,
What's
they all do. They all do. Yes, of course. Yeah, no, they all do. It's just a
So-
question. We're in this one because it's a general. Yeah, this is not a academic exercise. This is what they do in order.
Oh, I know, but I guess the question is like, so, when we did our lab one checkout, we did have a checksum. Was that unnecessary because the hardware would handle that for us, or?
It was necessary in the sub gigahertz because it didn't.
So
Yeah.
sub gigahertz, the
Yeah, that's
802.15
raw-
dot
that's
whatever,
raw stuff. Yeah, that's raw
that does not have hardware error correction.
Not that I know of. The IEEE 15.4 with the CC 1352 does, because it's not raw.
So then
got
as a,
that
as
TI.
an so as an
Oh,
architect, would we need to include a checksum in our, packet structure, or is that unnecessary?
Okay, now you're asking me a question for which there's an answer, but I don't know the answer. Depending upon what I'm telling you is, if you're designing the hardware, you're adding the checksum somewhere. Yeah.
But this class is using the hardware, so.
So the Bluetooth and the TCP and the Wi-Fi don't need you to add packets because it's built into the system. Now the sub gigahertz depends upon the internal. Now this sub gigahertz, you don't need to add it. It's in there. This thing is.
Where do we go for that information to figure out which ones have hardware error correction and not?
Great. This is why the more open the architecture is, the better. So you can see. I don't know the answer on the HC12. I actually don't know how the HC12 does encoding. Yeah, it's next year. I'll have that answer for you, because then I'd go in and use the network analyzer to analyze the field strength when it sends, so we can visualize the packets in the field with a sniffing antenna. Bluetooth and Wi-Fi and Wi-Fi and internet and Ethernet, all those things have error detection, not necessarily error correction, but error retransmission.
So do they automatically would resend the data?
Yep. Or fail, right? They could fail. Yep. The point is, there's not necessarily any one algorithm that's best, but the green one here is mostly good for any given hardware. You can see that they have different responses. And this was actually the question that Keyshawn asked a couple of slides ago. If you want to do averaging, you've got to double you may have to wait longer, but you do have your bit rate, which doubles the amount of energy in each bit. But fortunately, it doesn't double your noise, because the noise is typically uncorrelated. The noise only grows by the square root of 2. So if you do double the listening time, you do get an improvement in E over B. EB over N0. I don't know why I put this at the end. I moved it up earlier. It probably should have started there. Some of the errors occur in multipath. Okay, so you've got a signal from a tower to your phone. You might have a direct line of sight pathway, or you might have a reflected pathway. And just capital T here is the width of the pulse that it's encoding. And if you compare the spread delay D is the largest difference in time that largest difference in time that the packet may show up to the receiver from the same transmission packet, but in different times. And depending on the frequency and whatever, that packet may overlap, right? The delay spread may overlap the transmission, like the low frequencies. The low frequencies, short wavelength, long wavelength packets will have a packet width which is larger than the spread, but the faster frequencies will actually, the packets will show up not out of order, but yeah, pretty much in the wrong spot. And so this is the multiple path reflections is one of the noises that the receiver has to deal with. And so here's some terms that you probably gotta at least keep on a narrowband communication. This is obviously wireless. Narrowband communication versus wideband. And the narrowband, that's not the frequency, but the range of frequency, right? So the range of frequencies here that it's going to deal with is very small compared to the so the coherence bandwidth. You see, here's another bandwidth. The coherence bandwidth, this thing here, is 1 over the time over the delay spread. Okay, so the delay spread that we saw from the previous slide is the time differences from various paths. And so depending upon whether, in this case here, in a narrow band, all of the delayed paths show up in the same bin, okay? And where the coherence bandwidth here includes the frequencies, whereas in a wideband, Wi-Fi, Bluetooth, all those gigahertz range, it's out of band. The coherence bandwidth is smaller, so the delay is bigger, if you like, than the signal. So you're comparing this little, it's hard to see it, but this little waveform here represents the frequency of the signal that we're sending. This is the transmission bandwidth, the transmission power versus frequency. And it is the difference between wideband and narrowband is the relationship between the signal spread here and the coherence bandwidth.
Does that matter for like self-interference? Is that the point of that?
Yeah, no, yeah. So the point is, if you see these two pulses, they're from the same packet, right? But they don't show up at the same time. Now, your ears are pretty good at distinguishing sound that shows up at different times in your two ears, right? Because your ears are not in the same space and time, your brain can take two received audio signals and combine them in a way that makes sense. That's how you can close your eyes and hear where things are from, right? You can sense the direction of the sound from the delay in the signal processing inside your audio, inside of your audio brain function. But in this context, the receiver has no knowledge of the reflection path, right? And no knowledge of the two different distances for which it traveled. And this is a noise that it has to resolve. It can't It just needs a different way to process this as a single packet. Whereas this is easier to process because you basically don't have to process it. The two delays show up pretty much at the same time, and you just sort of look at the total signal. Whereas these, you have to, you know, sort of do something to get rid of the reflected paths or add them in ways in which this is the general. I'm at the end of this chat. What time is it? Okay, I'm way past time. So this is the last slide. Lower frequencies penetrate. Okay, let me start this because I want to talk about why. I'm gonna. Yeah, I'm about ready to. Let me start this one. I want to stop, physically stop. I'll review this a week from today after the quiz. So, any questions about? Yeah, about things.
Yeah, just real quick back to, so like in optical imaging, if we have a coherent laser source, it's good if we're within the coherence band of the laser because we get interference and that forms a meaningful signal.
Yes.
But you get constructive and destructive interference.
Yeah.
If the laser goes, if you're outside of the coherence range, you just get diffuse light.
Yep.
So I'm a little confused. So if I'm in the,
you know, no, it's not. It does. It just. You know, you're not trying to image. You're trying to detect.
Well, the point is you get constructive and destructive interference. So if I'm for the previous slide, would I not get destructive interference if I'm within the
bins? Absolutely. I'm just saying it's a problem.
So T greater than D is not good.
It does. It's not like it doesn't work. It just that is the essence of why the lower frequencies go further. They have less effect of the path lengths. Yeah, and I don't know much about lasers, so I don't know how well the analogy holds or doesn't hold. I'm just guessing it does, but it's not a good thing. Yeah, this is an error. This is not good. This is a bad thing. Well, it's a bad thing for wideband. All right, let me, yeah, since we are coming up on a test. Okay.